Everyone, welcome to 6.3. Today we're doing 6.3 and 6.4. 6.3 is working with normally distributed variables. So what I've done in this section, they've got this empirical rule and the picture. This is the exact same picture that we saw in chapter 3. And as you can see at the bottom of this box, it says these properties are illustrated together in figure 3.9, meaning it came from chapter 3. So I'm just showing you that, hey, we've seen this in chapter 3. We're seeing it again in chapter 6. But as a review of the empirical rule, remember it's a bell-shaped curve, which we see there. And what they're saying is approximately 68% of the observations are within one standard deviation of the mean. Approximately 95% of the observations within two standard deviations of the mean, and approximately 99.7% of the observations within three standard deviations of the mean. So there's a picture of it. So if I go the mean plus one standard deviation, I get here, minus one standard deviation there. So within these two, about 68% of the observations in here. And then similarly within two standard deviations, we have the 95%. And within three, 99.7% is our approximate value. Okay, so we're gonna use those ideas. So we're going from there and we're gonna build onto that. So let's actually see how we can actually find some of these probabilities. So here's a problem I've put down on here. So problem 699, New York City 10K run. As reported in Runner's World magazine, the times of the finishers in the New York City 10K run are normally distributed, so bell-shaped curve, with mean 61 minutes and standard deviation 9 minutes. So right away, we know mu equals 61, and sigma, the standard deviation of the population, is 9. Those are both in minutes. We also know it's a normally distributed curve, so we know it's a nice bell-shaped curve. Okay, so part A, determine the percentage of finishers who have times between 50 and 70 minutes. Well, we did this in the last video, but let's do it again real quickly so that we can see what's going on. We know if we were here, there's 61 minutes. We want to know between 50 and 70 minutes. So by our property of this being a density curve, we know that area under the curve is going to be equal to the proportion, which we can just change to a percentage. So all we're going to do is we're going to jump into StatCrunch to do this. So let's go here. Let's jump into StatCrunch. So I've got these values up here. I'm just going to go open up StatCrunch. And let's do this. So sometimes it'll give us this message and say, hey, you have to buy access. Well, I already have access. So sometimes we just have to press the button again. And it didn't come up. Let's try one more time. If it doesn't come up, which it's not, we'll just go into homework and exams. We'll pull it up from there where we've done it before. So I'm going into chapter 6. I know towards the end, we've got StatCrunch problems. Let's see if this is one. So I'm just randomly picking a problem. My goal is to get StatCrunch, and it's right here in the question help. That should pull it up for us. There we go. And now remember, to use StatCrunch to find this, we go into stat calculators and go down here to normal because they told us it was normally distributed. All right, so let's see. So the mean, what'd they say? That was 61. So the mean is 61. The standard deviation was 9. And we want to find between, what was it, 52 and 70? I don't remember what the problem was now. Well, yes, I need to go pull that up. Let's see. Oh, between 50 and 70. Ah, that was easy enough. So between, we have to click between 50. Oops, the negative's still there. Let's go back. Between 50 and 70. And all I hit is compute, and it's going to give me the value. Oh, my value, 0.7305. Usually we go to 4 decimals with the probabilities. So I will, in this case, sometimes I'll have to go to 3. Just pay attention to the way the questions ask, if they are specifying. If I'm going to go to 4 decimal places, the 5, the next digit not 5 or greater, so I don't round up, I just leave it at 0.7305. Okay, so let's go back in here, 0.7305. Easy enough. Now I want to do one with finishers who have times less than 75 minutes. Well, again, there's our normally distributed curve. It looks a little left skewed, but we'll just pretend it's close enough. 61's still in the middle, so 75 must be over here someplace. And I want to know the people or the percentage of runners with times less than that. And again, it said percentage, so I have to move the decimal here. 73.05% would be the answer here. Okay, now this one's less than 75 minutes. There's my 75 minutes. So I just go back to StatCrunch. What we had, 61 and 9, so I had those numbers right, and then less than 75. So now it's standard, and it's less than 75. 0.9400, again, the next number is 5 or bigger, so I round up, 9401. .9401 or 94.01%. Let's do this. That kind of got lost in the shuffle. We'll move it over here. 94.01%. There we go. That's better. And now obtain and interpret the 40th percentile. So let's see, this was A, this was B. Let's talk about C right here. Here's what it means. The 40th percentile is the place where you're faster than 40%. They're not going to go faster. They're going to go this way. The 40th percentile, that means we've got a 40% here. I don't actually remember which way this problem is designed to go, but typically the 40th percentile, you'd be better than 40%. So their time in this, since we're measuring time, their time was better or longer than 40% of the people. So we have an area to the left of 40%. We're trying to find this score right here, this X value. I don't know what that is. That's what I'm trying to find. So now I go back, and this is what we did last time when we were talking about Z of some number or finding the Z value. Well, it's an X value, so the only difference we're going to do is we're going to go back into StatCrunch. Instead of having 0 as the mean and 1 is the standard deviation, instead of it being a Z value, this one is an X value. And then we want the area, we want that to be 40%. So we do it this way, and let's make sure the picture is correct. Yeah, so there's the picture. The area is less than 40%. Remember, at 51, it'd be right, I mean, at 61, it'd be right in the middle. That'd be my mean. So it's left of that. So that's 40th percentile. It says, oh, the X value or the time, I'll go to 1 decimal place, 58.7 minutes. You could go to 2 decimal places. You'd round up to 58.72 minutes. But oftentimes they just round to 1 digit more than what the data is if you're finding numbers. So we'll say 58.7 minutes. And we're done. All right, so that's the idea there. That's what we wanted to do. So let's look, since that was pretty quick, let's get another problem so that we can kind of have a little more practice on this. That did not work out well. We'll say, okay, so let's go grab this. It's problem 102 that we're going to do. So let me go into my files, and I will grab down here, problem 102. There it is. Let's try this again. Copy. And go back and paste it in. There we go. Elephant pregnancies. G. Whitmire et al. Studied demographic data on African elephants article, comparative demography of an at-risk African elephant population. Based on this study, we assumed that the time between pregnancies of the African elephant in Kenya for elephants that have more than one calf is normally distributed, in bell-shaped curve, with mean 4.01 years and a standard deviation of 0.94 years. So if we were to graph this, it's normally distributed. The mean, the average pregnancy time for an African elephant living in Kenya, 4.01 years. I thought 9 months was a long time. Standard deviation of 0.94. So mu, 4.01, sigma, 0.94, or just 0.94 if you want to write it that way. Okay, so that's what we have. Now we're ready to go on to the questions. So the first question, notice it says, determine the percentage of such times that are less than 2 years. All right, so let's try that. So if the average is 4.01 years, how many elephants actually have their offspring in less than 2 years? All right, well, let's see. So graphically, what we're looking for part A, remember 4.01 is here in the middle, we want to know less than 2 years. So we're looking for that area, which is going to give us the probability. We'll change to a percentage. All right, so let's check. So let's go back into StatCrunch to do this for us. Does it real easy. So I'm in StatCrunch. We've got the right kind of picture. We just need to change this a little bit. So the mean was 4.01. The standard deviation was 0.94. So notice a big standard deviation, almost a whole year. And we want to know the fact that this X value was less than 2 years. So we just compute it. There's the picture, just a little area off to the left, so we know our picture's right. And the probability, if we go to 4 decimal places, it's going to be 0.0162, and I don't round up. So 0.0162. And then if I change that to a percentage, just move the decimal 2 places, 1.62%. So not very many of these elephants are going to have their offspring in less than 2 years. All right, now let's jump to the next one. And part B, let's see between 3 and 5 years. Well, that's not working real well, is it? Move this down a little bit. Between 3 and 5 years. Again, I like to draw the picture so that I don't know what I'm doing, especially since then I can compare it to, here, let's see if we can do this. Nope. I compare it to the picture that I get on StatCrunch. Again, 4.01 here. Well, 3 to 5 is almost, well, I put that in a bad place, didn't I? 3 to 5 is almost exactly splitting it. Let me erase this dot there. Okay. So 4 is almost exactly in the middle of the 3 and the 5, and since the mean was 4.01, that's almost exactly there. So that's what I have, and that's what I'm looking for. So essentially, I'm looking for the probability X is between 3 and 5. If you wanted to write it out that way. So I can do it. So we go back to our problem, back in the StatCrunch. It's going to do all the number crunching for us. And we say between, so click on between, 3 years and 5 years. 0.7125, round up, 7126. .7126, again, change it to a percentage, 71.26%. So pretty quick, you just have to understand what you're doing and how to get the answers. Okay, that's actually the end of that section. We had a couple examples there, so that was nice. Let's go into this next section, 6.4, and as you see, I've already put something there. All right, so 6.4 is called Assessing Normality, Normal Probability Plots. Let's read what this has to say. Guidelines for assessing normality using a normal probability plot. Let's back up for a second and talk about why we would want to assess normality. Anytime we're finding that area under the curve where we're using the z-curve to find those areas, that's based on the fact that it's a normally distributed population. It's a bell-shaped curve. If it's any other population, I can't find areas that way. I can't use that normal curve or the z-curve to find areas, so I can't find the probabilities. A lot of the tests that we're going to do later in statistics are based on the fact that we have a normally distributed population. So it's very often critical that we know whether or not the population is normally distributed, so we know if we can find probabilities that way using the z-curve. We know if we can run these other tests. Okay, so that's why we care about determining whether or not a population is normally distributed. Okay, so to assess the normality of a variable using sample data, construct a normal probability plot. And remember, we don't have all of the data. If we have all the data, it's going to be fairly easy. We could do a histogram, we could probably do a box plot, and we can look, if the histogram is bell-shaped, we know that it's normally distributed population. But what if we only have a few data points in our sample? If we only have a few data points, there's nothing that we can do to get an accurate histogram to see if it's normally distributed, to see if the histogram is bell-shaped. So what we do instead, one other option is doing these things called a normal probability plot. Once we do it, notice the two dots there. The bullet points say, first one, if the plot is roughly linear, you can assume that the variable is approximately normally distributed. So we look, if the shape of the dots pretty much form a line, a straight line, then we can assume that the variable is approximately normally distributed. The second one says, if the plot's not roughly linear, you can assume the variable is not approximately normally distributed. So then you can't use the z-curve to find probabilities. You can't run these other tests that we're going to see. And it said these guidelines should be interpreted loosely for small samples, but usually interpreted strictly for large samples. But the power of this is we can determine normality with just a few data points. We can at least get an idea right away if we think the population, if that variable is normally distributed. Okay, so what I'm going to do is we're going to jump in and we're going to look at these. So I'm going to show you how to do them. We're going to jump into the homework actually, and I'll show you what to do. We'll do a couple problems in there. So let's see. So let's jump back here. And what I'm going to do, let's jump to problem 31. So this problem, notice 6.4. So this is a problem from section 4. They give us a normal probability plot right here. And they say, okay, a normal probability plot of the data from a sample of a population shown at the right. Assess the normality of the variable under consideration. Well, the variable kind of looks like it's going up and then straight and then curved a little. And we have to determine whether or not we think that's approximately linear or if there's too much curvature. And this one, not totally obvious. I would say there's a little, it looks like there's a definite curve to it. So I would say it's not linear, so it's not approximately normally distributed. And let's see. The relationship is not linear, so the variable under consideration is probably not normally distributed. Let's see what it says on this one, and we'll just get some ideas. So they were saying, yeah, that's too curved to say it's approximately linear. There seems to be a pattern to the curve. But what I want to do, let's do a couple of these because it's going to regenerate. So let's do a similar question. That one, again, too much curve down here. I'm going to say not linear, not normally distributed. Let's check. And so what I would suggest is just do a couple of these similar questions. So it's regenerating numbers for us. Again, that looks a little too not linear, so not normally distributed. No, see that one, look, they're saying here, you know what? That's pretty linear. So this one, you know, kind of a little loose there. They're saying, you know what? I'm looking at this. When they're looking at this, they're saying, you know what? That's almost linear. There's just a little bit of curvature to it, but not enough. So what they're going to say here is they're going to say, you know what? This one's really close enough to linear, that we can say it's normally distributed. And so we will say the relationship's approximately linear, so the variable's probably normally distributed. And so that one, they say that's linear enough. There's a little curvature at the end, but not enough to be a definite curve here. Let's try one more of these to see. Similar question. I'm going to erase that. That one is definitely too curved. So that one we're immediately going to say not linear, not normally distributed. So notice from that previous one, there could be a little curve to it, but if it's pretty close to a line, they're going to say that's close enough to a line. This one definitely more curvature than the last one. Okay, let's go into the next problem. This one we're actually going to build our own normal probability plot. And so it's going to look closest to one of these four. Well, here's what we do. There is, I didn't want to select that. That doesn't matter. What I want to do is I want to draw on this a little bit, because what we're going to do, my normal probability plot, is called a QQ plot. If you do it in Excel, if you're doing the statistics in Excel, it's called a QQ plot. If you do it in StatCrunch, it's called a QQ plot. So if we're doing our own normal probability plot, we're going to look for where it says QQ plot. And notice up here, they give us, here's the times up here. Click here to view page 1 of the table of normal curves, page 2 of the normal curve, page 3 of the normal curves. We're not using the table to do these. We're going to just have StatCrunch do it. So what I'm going to do is I'm going to open this up. There's my data. And I'm just going to open it up in StatCrunch, and I'm going to do the normal probability plot, which they call a QQ plot. So I open that up. We can erase all that. There's my data. So this time what I do is I go into graph, because I'm going to graph something. And down here it says QQ plot. Okay, so it says, all right, what variable? Oh, variable 1. That's my data. That's the only variable I have. The rest of them are all blank. Now, I will tell you, here's a key part to this. You have to click normal quantiles on the y-axis. And I'll show you that when we see the QQ plot. And that's the only difference you have to do, and then just compute. And so we have this. It's kind of going up here, kind of curved, kind of looks like this. There's my graph. Well, let's see which one that looks closest to of the ones they gave us. So what I'm going to do, let's kind of just sketch that real quickly. So I'm going to kind of sketch that. Notice it kind of looks like this if I sketch it, something like that. I think that'll stay once I go over to look at what I'm doing in the problem set. So we're here, we'll close that down. And what does this look closest to? Well, it looks closest to, not really D. I would say it looks closest here. It kind of curved around a little and then kind of tailed off this way. Now, one thing about it, notice the normal scores were on the y-axis. That's that box we clicked. Otherwise, we would flip the x and y axis, which we don't want. So I'm saying the answer is A, but notice it only goes up to 3 on the y-axis. If you wanted to make your picture look a little bit better, what you could do, if you care, when we're here, notice ours only goes up to 1.5. If I want that to go 3, click down here and say, oh, y-axis, go all the way up to 3. Oops, not the minimum, the maximum. Go all the way up to 3. And then when I graph it, it's going to look a little more like theirs, where it's a little flatter. So now if I draw it, it looks kind of like this. Now let's see how that compares to the one they had. It should look a little more accurate. But you're just trying to get which one of these 3 it is. So there's our graph. That looks much more like this. It's not going up as steep as it was before, so it's flatter. So it's clearly A, and we're clearly correct. All right. So now use the normal probability plot to identify any outliers. Well, if I look here, this isn't really an outlier because it's kind of pretty much in line with the rest of these. It's not really doing anything. Remember, an outlier doesn't really fit. Now, it's possible that's an outlier because it's a little far away from everything else. I'm going to say it doesn't really look like it has an outlier. And we'll check. If not, then we'll say, oh, it must have been that one, and then we'd go label it. But it wasn't an obvious outlier to me. And based on the probability plot, does the sample appear to come from a normally distributed population? This is pretty straight. With real-world data, you're not going to get anything typically that's perfectly straight. So I would say, yes, that looks pretty normal and looks pretty linear. So it looks like it comes from a normally distributed population. So I'll say yes, since the relationship between the expectancy values and absolute values is approximately linear, well, that's why we think it came from a normally distributed population. All right, so that is pretty much what you want to do. There's only 2 problems from that section, so not a ton going on there, but the normal probability plot, and we may see this later in the semester, where they're going to give us some data, and they're going to say, hey, do you think the sample came from a normally distributed population? And so the normal probability plot, or on here it's called the QQ plot, is a good place to look to determine, hey, yeah, it looks pretty linear, so it's normally distributed. Or no, it doesn't look linear, it's not normally distributed. I can't do this test that requires a normally distributed population. Okay, so I'm going to leave that there. I guess we can come back to our problem set here. Not really much I drew on this. It was pretty much just going in and going to the problems and seeing if it's linear, normally distributed population. It's not linear, not normally distributed. Okay, so that's it. So practice these up, and we will talk more next time.